Hi, everyone. My name's Alicia, and I'm here with Chariot Solutions, here to introduce you to our speaker, Martin Kleppmann. He is presenting Automerge, an open source solution that will hopefully save us from stepping on each other's digital toes. All right, Martin, take it away.
Thank you very much. It's very exciting to be here, especially speaking straight after Alan Kay, who's one of my personal heroes in computing. And I'm hoping that the things I'll talk about today will actually be in keeping with the principles that he talked about on like actually thinking about what computing should look like in a principled manner in a way that is actually good for users. So you might know me from this book, Designing Data-Intensive Applications, that I published a little while ago, but that's not what I'm talking about today. I would like to talk today about, well, let's start with a bit of history, because that's always a good bit of context. So web applications. I guess most of you will be familiar with how web applications are created. And so I could broadly break this into about two eras. There's like in the 2000s, a typical web app was a program that ran on a server, and you probably wrote that program in Perl or PHP, or later Ruby on Rails came along, or Java or Python, or then Node later on. Anyway, with all of these, you've got a program running on a server, and you've got some client software, which is a web browser, and that client software receives some HTML from the server, and it may submit forms when you press a button in order to change some data on the server, and that data would then be stored in a database. And then people decided that that was a bit too clunky, and they added JavaScript because it's kind of clunky if you have to reload the entire page on every single user interaction. And JavaScript means now we can have a richer client app running in the web browser, and we've kind of replaced the interface to the server now with a REST API where the server sends us some JSON instead of sending some HTML, and the JavaScript app then renders that into HTML inside the web browser client side. So if you think about what is actually happening now in an app like this, well, there's state in a lot of places, and this data has to get from one place to another. And so, first of all, in your web browser, you have the HTML document object model, which is like the state that the user can see. And we don't actually keep the application state in the DOM directly, because that kind of becomes very messy. Instead, what you typically have is the JavaScript app will have some state in some model objects, or you might use some kind of state management layer like Redux, for example. And that state then, from time to time when it changes, will get rendered into the HTML DOM from which it can then be displayed. Okay, so it means now we have these two different representations of data where the user input flows from the DOM through event handlers into the JavaScript state, and in the reverse direction, we have some rendering using, for example, React or any other tool that you like. But now that's not all, because, well, the JavaScript app has to fetch its data from a JSON REST API somewhere. So you've got some HTTP requests going to a server, which have to be encoded as JSON, and the result has to be decoded from JSON back into the JavaScript application state before you then render it into the HTML DOM. But now if you think about what is happening on the server side, well, the server side is receiving these requests through the REST API, and it probably has some logic, some business logic that encodes how the state is managed. So it'll have some model objects, models in the sense of MVC, in your favorite programming language. And these model objects will get updated based on the information you get in from the requests. And they then need to be encoded as JSON as they go back out again. But in the model objects, it's not actually how you store the data. You also need to store the data in a database, and the database has its own data model again. So you probably have some kind of object relational mapping framework which converts between the model objects and the database. And then, of course, the database itself has to do some I/O on disk and on the network in order to actually store the data. And so if you think about this, here we've got 6 different representations of the application state. And most of our code is just converting from one representation to another. Like you must really, really like converting data from one representation to another if you have data in 6 different representations. And most of your code is really just doing these translations between all these different layers. And occasionally you have a little bit of application logic in between there. So this is kind of terrible. Also, there are other things that are terrible with web apps. Let's look at what happens when a user clicks on a button. Okay, a user clicks on a button, triggers an event handler in your JavaScript app. What does that event handler do? Well, it has to contact the server, I guess. So it makes an HTTP request to some backend server, and that backend server will have some handler, which then talks to the database, does some queries, maybe saves some state back to the database, and so on. While this request is ongoing, well, what is the JavaScript app doing? Well, the user clicked the button, and now you have to show them a spinner. And we have to wait. So you keep showing the spinner because this HTTP request has got to go over the network, and it's potentially going to go to a different continent, and the speed of light is very, very slow. And so you keep showing the spinner, and sometime eventually the HTTP response comes back from the server, you get a callback in the JavaScript app, and you update the button to say, okay. So this worked, but it was kind of unpleasantly slow because we were waiting for the spinner all of this time. So people had this genius idea, aha, what if we do something called optimistic UI? So that is, we're actually going to update the button to immediately say, okay, even before the HTTP request has even been sent, let alone the response has been received. And that's now, from the user's point of view, it's much faster. You click the button and it immediately says, okay. Except, this is called the optimistic UI, except what of course could happen is, well, you click the button, you set the status flag to okay, you send the HTTP request, and the request doesn't get through. Maybe you're on a coffee shop Wi-Fi and the Wi-Fi has just decided to drop all of the packets right now, and your request is not going to get through. And also you're in a part of town right now where the cellular data reception is kind of bad, so you just not be able to, you will not be able to connect your web browser to the internet right now. Like any requests you try to make will simply not go through. And the only thing your app can do at some point is then time out, call some error callback, and then update the user interface to say, actually, sorry, we said it was okay, but actually it wasn't okay because we were doing this optimistic UI thing, and now we have to somehow convince the user that actually they will have to resubmit their data sometime later, but maybe they're on a different page by now. Oh my God, this is terrible. There's a reason this is called optimistic UI and not realistic UI. So what I would like to propose is a different model, fundamentally different model for thinking about this type of software. And we have coined the term local first software. My collaborators and I came up with this word a little while ago, and I will explain now what I mean with this. There's an article you can find at this URL if you want to read more about like our thinking behind local first software. And local first software stands in contrast to the traditional web app model, where in the traditional web app model, there's a database on the server side, and if some data is not stored in that database on the server, it didn't really happen. Like the client might have some state, but you assume that the client state is basically ephemeral and basically might get thrown away at any moment. And if you want some state to actually persist, it has to go in the database on the server. Of course, this means now if you can't reach the server because you're on an unreliable coffee shop Wi-Fi or for whatever other reason, you can't do anything. You can't work offline. The local first model changes the priorities around. And we say, rather than making the server database the primary store of data, we use local storage on the client, and we treat the client's local storage as the primary storage of the data. There still might be a server, but a server's purpose is only to enable sync between different users and providing some convenient backup and so on. And the nice thing in the local first model is it doesn't really matter whether your device is connected to the internet right now or not, because your local storage on your local disk is always available, unless you run out of disk space or you have some serious hardware problem, in which case you have bigger problems. Generally, you can always write to the local disk regardless of what your network is doing right now. And so this means now in the local first app, when the user presses a button, you have the event handler, you write some data to your local storage, and you immediately update the status to say, okay. And this is not optimistic, this is true, because we've stored the data, and it's okay. It's fine. It's not going to become unstored later. And then at some later point in time, in the background, we can have a background process which syncs your local storage with the data that is stored on some server. But the user interface does not have to wait for it. This is just a background process that happens without any user interaction at all.
Sorry, Martin, to interrupt. Are you meant to
Yes.
share your screen?
Oh, can you not see my screen?
Yeah, sorry, I wasn't seeing it. Sorry about that.
Oh, no. I didn't see any of my nice slides. Okay, I'm so sorry about that.
Don't worry, there's still time.
Okay, can you see them now? Wait a moment. Can you see them now?
Perfect. We've got it. Thank you.
Okay, well, I will then just jump back very quickly, recapping everything that I said. If you will just excuse me the repetition. I was talking about the contrast of the 2000 style JavaScript free versus adding JavaScript. And then we have the 6 different representations of data that I walked you through, which is kind of terrible. So what we now want to do is look at what happens over time. So we have the event handler from the JavaScript. We have the HTTP request handled by the server. And now we have the long wait, the spinner in the web browser, until finally the response comes back from the server. And then we update the user interface to say, OK. Then we have the optimistic UI, where we say OK immediately. But in this case, of course, it could happen that things go wrong. The coffee shop Wi-Fi let you down. And in this case, you then have to update what originally said OK to now say, oh, actually, sorry, it wasn't OK after all. So we come to local first software, and this is the URL that I mentioned. As I said, local first software is a contrast to the traditional web app model. Rather than making the server the primary storage of data, we have the client's local storage as the primary storage of data, which means that it doesn't matter if the client is online or offline right now. We can always use local storage. This means now when the user presses the button, you have the event handler, you store the data locally, which is fast, and you immediately update the button to say, OK, and everything is fine. In the background, we now have the sync process that happens. Coming back to this 6 different representations problem that I talked about earlier, now if we look at this in a local first model instead, the whole situation has become vastly simplified, because actually all we have to reason about is there's some state in the JavaScript app. We need to convert that state into the HTML DOM using React or something like that for rendering. And we have some I/O to the local storage and the sync layer, which can then take care of saving any data to the server. But this is now a beautiful thing, because we have radically reduced the amount of code and complexity in the system by just getting rid of the server-side logic entirely. We've still got a server, but the server is a generic thing. It's just there for data synchronization. And the same server synchronization logic can be reused across many different apps. You don't need custom application logic on the server. Maybe you need a tiny bit for just doing very basic validation of the data, user authentication, those kinds of things. But all of the interesting logic, all of the user interaction, all of the data models and so on, all of that happens client-side. And because we have the client-side storage, it's fast and it's reliable. And this, I will talk more later about how we actually realize this data synchronization service. But think of it as a general purpose server. Like we can have a server implementation that is shared across any type of application, just like an HTTP server is a generic piece of software. You don't have to write your own HTTP server when you're building a web app. Likewise, you don't have to write your own syncing server for a local first app because it's a generic piece of infrastructure. Now, on the client side, local first software is beautiful because it's a much simplified programming model. You don't need to distinguish between whether the app is online or offline right now, because you're just writing to local storage, which is always successful. And the syncing, which happens only online, is a background process. We don't have this problem of optimistic UI where you might have to undo something, like you might confirm to the user something happened and then it didn't happen after all. You don't have any spinners because you're not waiting for network requests. You don't have any error callbacks on timed out requests, and having, like usually with every single server request you make, you have to somehow have the error callback, which then somehow communicates to the user that something went wrong. You don't have that if your syncing is just a background process. What we do have now is the additional challenge that, well, different users could be updating their local storage independently from each other at the same time. And we have to make sure that we handle that situation cleanly. And this is what Automerge is for. So Automerge is an open source software library that I've been working on for the last couple of years. It's part of my research. So I do academic research on this type of thing, but also I'm very interested in putting Automerge into the hands of application developers for building real software. And the best way I would say of thinking about Automerge is that it's kind of like Git, but it's not for source code, it's for the data of your application. And it has a data model which is essentially JSON with a couple of useful extensions. And so if you have a to-do list app, for example, you might represent the state of your to-do list app as a JSON document, something like this. So you've got a top-level object containing a key to-dos. Inside there's an ordered list of to-do list items, and each item has some text, and it has a Boolean flag whether you've checked the checkbox or not. And this state you can represent directly in Automerge. And what Automerge does is every time you want to change this state, you don't just update a variable, but you call a function called automerge.change. And this is very much like making a commit in Git. So it's a way of recording the change that you want to make at one particular time. That change takes effect. So in this case, for example, we take the to-dos 1 and set its done field from false to true. So it's a state update. But we also record a bunch of things about this change. And so Automerge is built on an immutable type of data structure. So that means you pass in the current state of your application as before, and that state is not mutated, it remains there, and you get back an updated state which reflects the changes that are made within this callback. You can attach optionally a commit message or like a change description message to your change, just like you would with a git commit message. And then inside this callback, the doc object here is a special proxy object that records all of the changes that you make. And so whenever you update any field here, this is recorded, and Automerge takes a note of exactly what has changed, and that uses that information then to sync that data with the server and with any other clients. So another thing you might also do with a list like this is you might insert a new item into the to-do list. So maybe I need to do the laundry, and so I'm going to call the doc.todos.push. .push is just a JavaScript function for appending an item to an array. And I'm going to pass this new JavaScript object into it, and Automerge will add it into the document, as you can see here in red. So you might ask now, okay, well, what if two users update the document concurrently on two different devices? And of course, this can happen, especially if people are offline, because, you know, if I'm offline and I make one change to my to-do list, which is shared with my partner also makes a change to the to-do list on her device while she's offline, and then sometime later we synchronize our devices. We need to make sure that everything remains in a consistent state. And so for this, we borrow again from Git, and Git has this model of branches which you can merge. And very similar to that, in Automerge, we also have chains of commits, chains of changes, which can branch and which can merge together again. So if you start off, let's say we start off with the state here where we have to do two items, and the user A changes it to set the watering plants item to true, while user B adds do the laundry as an additional to-do item. And so when these two branches get merged now, well, it's kind of clear in this case what we want to happen. We want the water plants to be set to true, and we want the item of doing the laundry to be added to the list. And so in this case, I think it's fairly unambiguous what a clean merge of this data looks like. And Automerge performs this kind of merge automatically. That's why it's called Automerge. In particular, there are a few guarantees that Automerge provides. And those are, firstly, if you make a change, then that change is always preserved. So we don't throw away any data. That's kind of useful. Moreover, if two users have seen the same set of changes, even if they saw those changes in a different order, then they will always be in the same state. Or put another way, you can take any two branches, and if I perform a certain merge and my partner performs the same merge between the same two branches, the merged outcome will always be the same. So this is different from Git, because in Git, you would have an explicit merge commit, and you might have some conflicts which occur while doing the merge. And those conflicts have to be resolved manually by you, the user. Whereas in Automerge, it's different. Any merges happen automatically because there is a well-defined procedure that always lets us merge two branches together, regardless of what has happened on those two branches. And I will show you shortly why that makes sense and why this is a safe thing to do. So because we have these branches and we have these different versions, and we can refer to the document state at any point in time that it was, just like with Git, you can look back at what the state was a few days ago, and you can compare different states. Like in Git, every change in Automerge is identified by its hash. We use a SHA-256 hash of the change, and every change includes the hash of its predecessor changes, which might be multiple hashes if it's a merge. And in all of these cases, we can see what was the document state at one particular point in time. So you can, for example, visualize what changes the other users have made. All of this is possible, especially the merging is possible, because Automerge is something called a conflict-free replicated data type, or CRDT. And so this is there's a whole bunch of interesting academic research on CRDTs, which are these data structures that allow several users to update them concurrently and which always guarantee a clean merge at the end. So I will explain to you a bit more in detail on how Automerge works and how it enables this kind of clean merges using CRDT techniques. So the way Automerge works is when you call this automerge.change function and you make some mutation to the JSON document, we record all of the changes that happen as operations. And there's essentially a log of operations which are very fine-grained updates to the document. And so in this case, adding the to-do laundry item to the to-do list consists of first making a new map object, that's the curly braces, and we link that object into the existing to-do list object through a mechanism of referencing IDs, which I'll explain in a moment. We insert that as a new item at the end of the list. And then we created an empty map, so then we assign two keys within that map, the title key and the done key. The title key has the associated value of do laundry, and the done key has the associated value of false. Now we have this operation log. Next, Automerge uses a custom binary encoding, a compressed binary encoding, to represent this log of operations in a very compact, efficient way. So what we get back is a byte array. And this byte array, you can then do anything with it. You can write it to disk using your favorite storage engine. How exactly you write to disk will depend on whether you're running in a web browser, in which case you might use IndexedDB, or if you're running in a server that has access to the file system, in which case you can just use a regular file, or you could use a database, whatever you like. It's a byte array, you can store it anywhere. And of course, you can send it over the network as well as part of a sync with other users. So when we construct a new object like this, we do this by constructing an empty object and then assigning the individual fields within it. Later, then we might come along and want to update one of the keys or one of the properties in this object. And so if I now want to set done to true, well, what happens here? First of all, look at these object references. So when I create a new object, like in this case, a map object, that object gets an ID, which is a unique ID that's assigned by Automerge. You don't have to worry about how exactly they are generated. And then later, when you want to update that object, you can reference that ID. It's a globally unique ID, so that we know which object we're talking about. And then likewise, later on, when we you can see when we update the to-dos 0 item, the object that we update is again the object 1A. Secondly, each operation that sets a key to a value also has an ID. And so in this case, the ID that initially set the the value of the done field to false, that initial operation had an ID of 3a. And later on, when we now update the done field from false to true, the operation has an ID of 4a, and it indicates that it overwrites the prior operation with ID 3a. So this is how we know that which update happened after which other update. We make this explicit relationship between one operation for setting the value and the prior operation. And we say that here, the setting done to true overwrites the previous value of setting done to false, and therefore it's clear the value changes from false to true. However, what could happen is that two users actually set the same key, the same property, to two different values. Let's say we want to introduce a deadline feature into our to-do list app, some deadline by which some task needs to be done. And so in this case, user A sets the deadline to the 10th of July, and user B sets the deadline to the 14th of July. And in this case, there's nothing we can do to merge these. These are just two different values which are in conflict with each other. So in this case now, the name conflict-free replicated data type is a slight misnomer because there is actually a conflict. And the way we represent this is that, well, we have two operations. Those might have IDs 5a and 5b. Each of those operations sets the deadline to a particular value. We have two different values. But if you look at the overwrites field is empty in both cases, which means that neither operation overwrites the other. And from this, we know that the two operations are concurrent. Neither overrides the other, and so therefore we have to keep both of the values. And this is the only case in which Automerge actually exposes a conflict to the user. So only the case where two users update the same property of the same object. In that case, we get a conflict, and you can call the Automerge getConflicts function, and it'll tell you exactly what the values were. And so then your application can decide, maybe it just throws away one of the values, or maybe it's actually going to show some user interface to the user and let the user choose what was the intended value. That's something that the application can then resolve as it wishes. But all of the other changes can be merged automatically. So if two users insert or update items in a list, or for example, those things can always be merged automatically. So I said Automerge provides essentially a JSON data model with a couple of extensions. So there's a kind of set data type, or a bit like a relational table. There's a counter data type, a timestamp type, cursor, which allows you to refer to a particular position within a list or a position within a text document. The text data type is constituted essentially of a list of characters. And so this means if you have text where you want users to be able to edit character by character and see like real-time edits like you would in Google Docs, you can do that using the text data type, and each character is then represented as a separate list element. And on top of these types, Automerge then supports a whole raft of operations. These are things you don't see normally as a user of the library, but I'm just mentioning it so that you can visualize a bit what's happening inside. So I showed you, you can create a key in a map. You can create an empty map. You can set a key in a map. You can delete a key from a map. You can create a list object. You can insert and delete from lists. You can update items in lists. If you have a counter, you can increment it or decrement it. If you have text, you can insert or delete characters from the text, and so on. That kind of makes sense. So what is interesting with this now is that using something like Automerge, we can now quite easily build collaboration software. And what I mean with this is software in which you've got several users who are all editing some document or some piece of data at the same time, and you've got some real-time sync between them. So you can actually imagine a whole spectrum of different models of collaboration. At one end, you've got the Google Docs style. You can see every single keystroke of the other user as it's typed. At the other extreme, you have a very asynchronous form of collaboration like pull requests in GitHub, where somebody might prepare a pull request over the course of several days and then submit one big pull request which contains a whole bunch of changes. And you can imagine things in between. So for example, with Google Docs, you can have suggesting changes or change tracking in Microsoft Word or things like that, which is sort of like in between the two, where you're not immediately merging all of the changes, but you're providing a bit of user control over when the changes are accepted. And the Automerge is designed in a way that gives you the flexibility to choose any of these models of collaboration, whatever suits your application the best. So if you're doing real-time collaboration, this means you're accumulating changes very quickly, because like in text editing, for example, every single keystroke is going to be a change operation. So you can accumulate hundreds of thousands of operations, and part of the challenge is then making those kind of large change histories efficient. But if you want more coarse-grained changes, you don't want to show every single character as it's typed, that's totally fine too. So the programming model for this is very important. So we talked earlier about you can represent the state of your application as an Automerge document, as JSON essentially. Now we need to integrate this with the rest of our application. And many JavaScript apps built nowadays use something called React, this library called React, which has popularized a style that is sometimes called functional reactive programming. And so in this style, you have what is essentially a one-way data flow loop. And this is a very useful property for keeping the complexity of an application manageable. And that is, as I said earlier, we have at least two representations of our data. We've got the DOM, which is a stateful object, and you've got your JavaScript application state. And React provides us with a principled way of converting from your application state to the DOM. So if something changes, some piece of state in your application changes, then you always make that change to your JavaScript application in-memory objects first, and then you call the render function, and the render function updates the user interface accordingly. You don't go in the reverse, so we don't like make a change to the DOM first and then somehow retroactively attach it back to the document. That would be very confusing. So instead, we make the change to the model objects. We re-render the user interface. React does that efficiently. The user can see that interface. They can click something or they can interact with it, which calls an event handler, which again updates the Automerge document. So this is just existing React stuff. We didn't invent this, obviously. But we can integrate Automerge with this React model of programming, and the result works really nicely, which is now when you are syncing with a server, well, of course, if you've made some changes yourself, you will send those to the server, but you may also receive some changes from the server because there might be other users who have also been updating this document and they've been syncing with the server. And so you might receive some changes from the server. So maybe a different user, for example, sent you this change that they set to do item 0, the done field, to true. And so this change will now make its way to the server via the sync protocol. And then this will be reflected in the Automerge document state on your local device. And then we just do the regular React rendering thing to update the user interface, which will mark that item as checked, that checkbox as done. as done. And here we've suddenly got real-time collaboration, and we have had to do no extra work for it whatsoever. We've just used the existing React render loop, and we've hooked in the possibility of receiving changes from a remote server via a sync protocol that is implemented by the library that we don't have to worry about. And we just get the streams, the changes from other users streaming in, and it updates our user interface. It's beautiful. We get this real-time updates and collaboration with no extra programming effort at all. Now, the sync protocol is designed to be very general and to work with any type of network topology. And so I've been talking about syncing with a server, and you can certainly do that. You can have one server and sync with it, and that is totally fine. But you could, for example, also have multiple servers. You could imagine some kind of federated system, like email, where you have multiple email servers which can interoperate. One user on one email server can send an email to a user on a different email server, and they use SMTP between the servers to communicate. Likewise, the Automerge sync protocol can be used not just between a client and a server, but also from server to server. It's exactly the same protocol. Moreover, you could actually have sync directly between users using a peer-to-peer protocol. Or it means that if you've got two devices which are right next to each other, they could use something like Bluetooth or a local area network in order to sync changes between the user devices directly without even going via any servers at all. So this is wonderful because it gives us a lot of flexibility in terms of how we actually deploy the system. And it means that, for example, if one of the servers goes away, that's fine, we'll just keep using the other server. Then the server is not like this linchpin, this central point of failure, the single point of failure that you typically get with typical web apps. You might ask, one problem with this is, well, what do we do about access control and permissions? Like, you can't just send any data to anybody, because sometimes you only want some users to be able to access this data, and not everything is public, obviously. And so I will warn that this is a work in progress. So Automerge itself does not have any built-in security model. This is something that you do at the networking layer separately outside of Automerge. But we have a bunch of work ongoing on ways how you can achieve access control. Firstly, you have to ask of, like, how do you ensure that only the users who are supposed to be able to read some data can read it? And one way of doing that is just the centralized server way, which is exactly how you would do it with a traditional web app, which is you authenticate to the server some way with a password or some two-factor authentication or whatever you like, and the server gives you the data if you authenticate it correctly. Fine. Of course, that doesn't work in a peer-to-peer setting, because if you're talking to another peer, you don't have the server as an authority to do the authentication. But one way of doing it in a peer-to-peer case is, say you have a shared secret URL, and if two users know the same URL, then they're allowed to sync with each other, but you won't sync with another user who doesn't know the URL. That's one way of doing it. We've been doing some research actually on having a better form of access control lists, which is still decentralized, which still doesn't depend on a single server as authority, and which relies on encryption as a way of ensuring who can actually read what. But I don't have time to go into that in detail today, and just wanted to mention that as something that is going on. Besides reading, you will also care about who is allowed to update some data. And again, you can use the traditional centralized server model, which is just you send the server your changes, and the server looks at your changes and decides based on some rules whether they are acceptable or not, and it just rejects any changes that are not acceptable. But we can also do a similar thing in a decentralized, in a peer-to-peer setting, where actually every peer maintains the information about who is allowed to change what. And if you receive some changes from another peer, and that peer is not allowed to make those changes, you just ignore them. So you can never stop somebody from modifying their own local copy of a document. That would be meaningless. The copy, like the data is on their local computer. They can do with that data whatever they like. You cannot stop them from changing it. But if you don't like the changes, you can just ignore them. You don't have to pay any attention to those changes. So this is a way how we really have to change our perspective if we want to do this kind of collaboration in a decentralized way. Let me talk a little bit about how Automerge is actually implemented. So we started with a JavaScript implementation, and it consists of broadly two parts, which we call the front end and the back end. Though I should emphasize, this is not like front end is the client, back end is the server, as you would use it in a typical web app setting. Here, front end and back end are part of the same library. They're tightly coupled together. You might run them on different threads potentially, but they're intended to be run on the same computer, not across a network. And this is just a distinction that we make for convenience of being able to develop this library. So there's a JavaScript API that you can use. There are TypeScript bindings for those who prefer TypeScript. And we then decided, okay, we want to also try implementing the backend part in Rust, because Rust, apart from being faster, it also has the advantage of being a lot more portable than JavaScript. So with Rust, we can compile it to WebAssembly, and then we can actually use the existing JavaScript API with no modifications, where instead of implementing all of the hard CRDT logic in JavaScript, we now implement all of the hard CRDT logic in Rust. It's faster, as I said, but it also means that we can compile the same Rust to native code, and we can make Python bindings, for example. We can have C bindings and use that to expose a Swift API, so you can build iOS apps. We can do the same thing with Android apps, for example. And of course, we can have an API in Swift, and we can extend the set of supported languages arbitrarily, and we have a couple more languages in preparation. So this is very nice because all of this CRDT logic can get rather complicated, and we've got all of this stuff for binary encoding of messages that get sent over the network and so on. And so what we're hoping to do in the future is to have the Rust implementation as the primary one, put all of the hard stuff into the Rust code So we have to just implement it once, and then we can use that in a very cross-platform way to build apps that can interoperate regardless of what platform they're running on, because they're all speaking the same sync protocol. They all have the same data model using this protocol, using this platform-independent this Automerge library abstraction. Now, underneath this, there's a separate layer for the storage and networking. So Automerge itself is only a data structure library. It only deals with in-memory objects. It doesn't do any disk I/O. It doesn't do any network I/O, because the type of I/O that you can do in a web browser is very different from the I/O you can do on a desktop app or on a server, which is different again from the I/O you can do in a mobile app. So we've deliberately separated out the storage and networking concerns, which have to integrate with whatever local platform you're running on. But we try to move as much complexity as possible into the platform-independent part of the library. And the model that Automerge uses for the storage and for the network sync is essentially a log of changes. So when you're typing away at a text document and you're sharing it one character at a time, you're building up this log where we're typing hello one character at a time. And each of these changes is just encoded as a byte array. That byte array you can append to a file on your local disk, for example, or you can write it to IndexedDB, or you can send it over the network to a server or to any peers who want a copy of this information. And this works, and so this is essentially an append-only log, except the log gets quite long over time, especially if it's a text document and you're accumulating hundreds of thousands of updates. And so what we do then from time to time is take a section of this log and compress it down into a compact snapshot, which still contains the entire editing history, but just encoded in a way that makes use of the fact that a lot of the information about the relationship between these individual operations is now known. So we can make a compressed snapshot, and then on top of that snapshot, we can continue editing. So we can still just keep appending to the log, and so somebody's typing hello world, one character at a time. We just keep appending, and then when the log gets too long, we bulk it back together into a snapshot again. So you might wonder, how well does this snapshotting actually work? Like, isn't it really expensive to keep all of this history? And so we did some experiments. So the benchmark we've been using is a text editing document of a document which is actually an academic paper that I wrote with a colleague. And we recorded every single keystroke that went into the writing of this document. So it's a real document. It contains about 360,000 keystrokes that went into it. About twice as many character insertions as deletions. So you can see there was quite a lot of data that was added to the document and then deleted again. And if we represent this as a change log, we have like 35 megs or something like that of data, because each individual change takes about 100 bytes to encode. And it's still fairly big. However, if we use our snapshot compression that I talked about, we can actually bring this down to about 300 kilobytes. So we've reduced this by a factor of more than 100. And in the process, we have not thrown away any data. So this snapshot compression is completely lossless. We can reconstruct exactly the original change log, byte for byte identical, that we had originally. So this still contains the full editing history. You can still go back in time. You can look at different versions of the document. You can diff them and so on. All of the Git-like interaction is still there. What I want to say with this is it is possible to actually keep this change history for even quite long change histories in a way that is very efficient, that is less than 1 byte per change using this compression. And so this is what makes this kind of Automerge history management actually viable in practice. A few brief words about the current status of this project. So we're currently trying to get to a 1.0 release. It's working fairly well on the JavaScript side. The Rust implementation is faster than the JavaScript implementation, but not as well tested. But there are a couple of people starting to use it in production. I will warn that this is still early stage software, and it still gets slow if you have large documents. So this performance is one of the key things that we're working on over the next couple of months. And we have a long to-do list of stuff that we want to do with it. So it's by no means really feature complete, but we do have a lot of the basics there. So I won't run you through all of the long list of things that we want to do, but essentially this is all stuff that is planned. So just to finish this off, so I mentioned that this idea that with local first software, we can write applications in a way that is radically simpler than the type of software we have with traditional web apps. And that means we have essentially no server-side code because we have this self-contained client app and then a generic synchronization protocol using a generic server that can be hosted by anyone. A lot of the complexity of dealing with a networked application is just taken away because we don't need to distinguish whether the app is online or offline. We don't have callbacks to handle cases where requests to a server failed because the internet connection is down or the server is down or whatever. We don't have the problems of optimistic UI where you make some change and then have to roll it back again because all we're doing is writing to local storage. It's just radically simpler. Moreover, this type of software is much more resilient against failures because, say, if one cloud provider goes away, well, you just spin up a sync server on a different cloud provider, switch the URL over to that one, everything continues working. You can have multiple servers and syncing between the servers. That's all fine. So, with typical software as a service, there's this huge risk that, what if the service provider goes down, or what if they shut down, the company goes out of business, they discontinue the service, now all of our software stops working and you lose all of the data that you ever created with the software. With local first software, you don't have that problem because you've always got the data on your local device where nobody can take it away from you. Moreover, we can even use encryption so that any data that is stored on the servers is actually encrypted. So even if somebody hacks the server, they actually can't get anything interesting. All they will see is a bunch of encrypted data. So only the decryption happens on the client side because only the client side are actually working with the data. The servers are only just sending messages, forwarding messages around. And finally, but I think most importantly, I believe that local first software has the potential to provide a much better user experience because you don't have these spinners waiting for an HTTP request for a server to complete because the sync just happens in the background. The software just works offline. You don't have to do any extra work, and it works regardless of whether you're offline or online. You can do multi-user collaboration, and as I showed you earlier, using this functional reactive programming approach, it's no extra work to support collaboration. And finally, the users are in control of their own data. They own their own data because it's on their local device and they can do whatever they like with it. They have control and autonomy and agency over their own data, and this is something that I believe is very important. So thank you very much for your attention. Automerge is open source and you can find it and you can start playing with it if you like. You can read about our ideas on local first software. You can find me on Twitter. You can email me. And a huge thank you to the many contributors who have also helped make Automerge happen and who are continuing to contribute to it. So I hope I have a little bit of time for questions. And yes, thank you very much for coming along.
Thank you for that great talk. I do have some questions that are coming up, a lot of applause in chat as well. So the first question that's coming from Zoom chat, can Automerge sync between servers? Your talk is about web apps. Can it operate in a headless mode? And what about handling crash recovery?
Yes, so syncing between servers is totally fine. It works in exactly the same way as syncing client to server and in the same way as client to client, peer-to-peer. So we've tried very hard to not distinguish between those. The sync protocol, as implemented by Automerge, is an abstract protocol. That is, it just works with, there's one function which is called generate sync message, which gives you a byte array of the message to send, and a function called receive sync message, which takes one of those byte arrays and applies it to a document. So how you get those byte arrays over the network is up to you. So you can send them over WebRTC, you can send them over WebSocket, you can send them over a plain TCP connection, you can send them over HTTP, whatever you like. I don't care how you get the bytes from A to B. I think we will end up probably with a little set of accompanying libraries for Automerge, which just do that sync over a bunch of different transport layers. But all of the complexity is moved into the general purpose, the platform independent part of Automerge. And in terms of working headless, yes, absolutely, it works totally fine headless. The Automerge library is just a data structure, essentially. And so you can run it on a server in a Python process without any user interface at all, and that is totally fine. You can write a command line tool in Rust, and that's totally fine. You can write a browser-based app, compiling it to WebAssembly, and then running it in a browser. You can write mobile apps. In any of those platforms are fine.
And I think one last piece of that question was handling crashes in Automerge.
Oh, yes. So as I said, Automerge itself does not do any I/O. It's just an in-memory data structure library. So what happens when you make a change is you get back a byte array, and you should persist that using whatever storage technology you have available. So for example, you might append it to a file. You can decide whether you want to call fsync on that file, depending on the exact durability properties that you want. You can write it to a standard database or a key value store. And once it's reached whatever storage layer you're using, then you will be able to have consistency in the case of a crash. So Automerge itself, then if you want to reload it back into memory, you would just take whatever snapshots and log of changes that you have and replay it. And whatever you have in storage, you can reconstruct a consistent document in memory from that again. So just as long as you have some kind of storage layer which will reliably give you your bytes back again, then you'll be totally fine. There are checksums and stuff built into Automerge so that if there's any corrupted data, it won't accept it. So you have crash consistency in that sense as well.
Thanks. And for the askers, I'll prioritize Zoom questions because they're going to disappear. But there are a bunch of questions in Slack that hopefully there's time to answer after the talk.
Yes, absolutely.
Any thoughts on how to address the problem that clients may have user-controlled time settings with respect to sequencing of changes?
Yes, so Automerge itself does not depend on clocks at all. So there's one use of timestamps, and that is every change gets tagged with the system clock of the user who made that change. And that's purely a convenience thing, so that if you're looking through a change history, you can see what change happened. If the user's clock is set to something completely wrong, obviously that timestamp will be wrong, and there's nothing we can do about that. You will simply get an incorrect timestamp on a change, but as I said, that timestamp is purely informational. So the conflict resolution logic, the CRDT logic, does not depend on those timestamps in any way. And so the worst case is that if you're visualizing the change history, you end up with some confusing entries in the change history where it seems that some change happened 3 weeks from now. And in that case, maybe that's something that can be handled in the UI. But from like the algorithm point of view, it makes no difference.
Thanks. Does something like Automerge assume you are eliminating defining contracts at service boundaries? How do we guarantee integrity at each layer?
Yes, so Automerge is kind of doing away with the concept of services as they are traditionally used in web apps, because we're saying that everything is reduced down to this document state and how we can sync it. So this makes most sense for the types of applications where you've got a user editing some complex data set. And this could be a text editor, it could be a spreadsheet, or it could be a CAD drawing program or a graphics editor or something like that, where the user can essentially update any part of the data. I think this approach is less of a good fit for the types of enterprise applications where it's, for example, you've got a big database of orders that have come in, and you want to do analytics over the orders, and you want to generate invoices and things like that. I think for that type of data, probably the traditional service-oriented architecture approach or microservices approach is fine. And I think I probably wouldn't use Automerge in those contexts. So I would use it more in the context where you've got like a sort of document editing in the broadest sense.
Thank you. Moving into some of the Slack questions. What is a practical solution for resolving a very large discrepancy in the state between server and a user? Like one user loses a connection for a very long time and their state is quite divergent.
Mm-hmm. Yes, so that will be handled absolutely fine. So the amount of divergence from the point of the CRDT algorithms, really doesn't make any difference. So all of the same conflict resolution logic will still apply. So if you've got a bunch of, say we inserted a whole section into a text document, and that'll be lots and lots of individual character insertions, but in bulk it's still like, boom, here's a new section. And if two different users added a new section at the same place in the document, then the final merged result will contain one user's section followed by the other user's new section. So all the data will still be there, even if it is diverged by a lot. We do a bunch of work on the sync protocol level in order to efficiently handle resync of two devices that have gone out of sync substantially. So the sync protocol is such that you can run it frequently, and if not much has changed, then they will just exchange a few bytes to confirm, okay, nothing has changed, all fine. But if they detect that there's been a large divergence, then they'll package up a big chunk of all of the changes that have happened and send them all in bulk. And so that way you can then get efficient resynchronization even after they've diverged substantially over a longer period of time.
Thank you. What is the best way to stay aware of the progress of the encryption approach to access control?
The progress, well, I talk about it on like my Twitter. I have a blog where I write about these things periodically. You can sign up for email notifications when I write a new blog post. I even have a Patreon account, so if anyone wants to support this work, you can find me at Martin KL on Patreon, and I also send monthly updates to my supporters there on any new research that's happening. So, you know, as an academic, I write research papers besides the software that I write, and I find this actually a very valuable way of communicating our work, because, you know, a well-written paper provides a lot of background and the reasoning why we do things, not just what the outcome was. And for example, we do have a recent paper, which is available online, on a key agreement protocol, which is exactly for this purpose, for doing end-to-end encryption, providing very strong security properties, so providing forward secrecy and post-compromise security for end-to-end encrypted group collaboration. So I would refer you, I can put a link to that paper in the Slack as well afterwards.
Thank you. Do you have any thoughts or insights into the implementations that Google uses to solve these problems, specifically thinking about Google Docs and collaboration?
Yes, I have not worked at Google, but I've spoken to some people at Google about what they do. So they use an algorithm that is different from CRDTs. It's called operational transformation, which kind of achieves a similar thing to CRDTs, except that operational transformation, the way they do it, requires a single server. And so it's absolutely crucial for the conflict resolution to work that all of the communication between users goes via a single server. And in the case of Google Docs, Google hosts that server, and they make sure that if that one server goes down, they spin up a replacement and so on. So the approach we're using, Automerge uses CRDTs, which do not depend on the single server. They can use any network topology for the data synchronization, which provides us with a lot more flexibility. Traditionally, the trade-off there has been that operational transformation has been faster and more efficient. CRDTs have been more flexible because they allow any network topology, but they've also been slower. We are trying to overcome that. So my goal is over the next year or so to get our CRDT implementation to the point where it's at least as fast as any operational transformation implementation out there. I believe this is something we can achieve. And then essentially, I think CRDTs will have won. In that case, there's no real reason for using the operational transformation approach anymore, because CRDTs are easier to reason about. They're much more flexible. They allow any network topology. And if we can also make them fast enough, then I think they will have won.
Great, thank you. And our time is up. Thank you everyone for all the questions. Thank you, Martin, for your great talk. There are more questions in Slack where you can continue the conversation in #room-B.
Okay.
All right, thank you very much.
I'll be on Slack for a bit, and sorry about the mess up with the slides at the beginning.
Oh, no worries. It was a great talk. I actually didn't think you needed slides because it was so easy to understand. All right.
Okay.
Thank you.
Great.
Bye-bye.
Thank you.